Hi guys. Alright, so this is the video on section 4.1 where we started trigonometry. I went over these notes today in class and they're posted on EDSB already. But I'm going to do some more examples of what we talked about today. So again, trigonometry is just the measure of angles. I started out with a ray to kind of help you remember how we construct angles. So a ray is just part of a line. Sometimes it's called a half line. And it has an endpoint, which is usually given some label by a capital letter. And then there are many other points that make up this line. An array can go in any direction that we want it to. And we name a ray by its endpoint first and then some other point on the ray. Okay? It has direction. They can go in all different directions and whatnot. But that's not the big topic here. So the idea is we want to think about what is an angle. Angles are denoted with a less than symbol with an arc through it, so that way you don't confuse it with the inequality. But if we take two rays, so maybe I take this ray and connect them at their endpoints, then I don't want to change the direction, so I'm going to try and keep it as much the same as I can. Then what we do is we connect these two rays at their common endpoint, which is called a vertex, and an angle forms, and the angle is the measure in between the two rays. So down here, that's exactly what I have. I took a ray AB and a ray AC, and I joined them at point A, those endpoints, which is called the vertex of the angle. The angle measure is actually in here. And the rays now are called the sides of the angle. Okay, so each ray is called the side of an angle. We have side AB and side AC of this angle. We would call this angle, BAC. We could call it angle CAB, and we can even call it just angle A because the vertex isn't shared with any other angles. Okay, and usually when we denote an angle, we use a Greek letter. So in upper math, all we use is Greek letters. And theta, this is called theta. It looks kind of like a zero with a little, I don't know what it looks like. But anyway, that's theta. And theta is very common. Other ones are alpha, beta, phi, lambda, and there are many other ones. But probably theta, alpha, and beta are the ones you're going to see the most in the book. Okay? And what we're really interested in is not just any angle like from geometry, but we want to talk about angles in the plane, because what we do is, well, let me go here. If we have an angle in the plane, it's caused or created by a rotation. So the idea is, let me see if I can find a smaller writing utensil here. Maybe this thing would work. The idea is this, is that the positive x-axis contains a ray. It's like a ray from the origin to infinity, right? It's like a ray. And the idea is that we can rotate this ray any way we want to around the circle. So this is really bad. That's not working out. We can take this ray, we can rotate it to some place, so a stopping point. So we always start at the positive x-axis, and we can rotate it maybe counterclockwise and stop and draw where we stopped here, and we formed an angle like that. Okay, so an angle in the plane is formed by rotating the ray about its endpoint. The endpoint is always at the origin. Okay, and of course that's going to be the vertex of the angle now, right? So what I said in class is that this is called the initial side because it's the positive x-axis and it's sort of stationary until you move it. So this is the initial side, and the stopping side, the place where you stopped rotating at and drew the ray, that's called the terminal side of the angle. Okay, so again, the endpoint's at the origin, which is called the vertex of the angle, right? I've got my initial side, my terminal side, and by the way, my initial side is always going to be on the positive x-axis. And when we have an angle whose initial side is on the positive x-axis and whose terminal side is somewhere else here in the plane, we say that the angle is in standard position. So standard position. Okay, I could take my ray, so this one I went counterclockwise. I could take my ray and maybe swing it down over here and stop. So, you know, if I did that, if I went in the clockwise position this way, I'm going to call this angle something else. Then I have this other big angle here, right? And by the way, angles that go in this direction, counterclockwise, are always positive. Clockwise are always positive angles. And angles that go clockwise, so you form them by moving in the clockwise direction, those are going to be negatively valued angles. Okay, so you know this angle here I might say is about 40, well not quite 45, but maybe it's about 40 degrees. All right, it's positive because I rotated my ray counterclockwise. This one here, which is an obtuse angle, right, it's bigger than 90 somehow. I don't know exactly what it is, but you know I can kind of guesstimate. You know, a complete half turn would be 180 degrees, and that's, you know, I don't know, call it maybe, let's just say 140 degrees. So I'm just eyeballing it, but it's going to be negative because I'm going in this direction. Okay. All right, what else do we cover? Oh, coterminal angles. All right, so coterminal angles. As it says on the sheet, a coterminal angle is an angle that has the same initial and terminal side. So this little picture that I drew here is kind of says it all. I can take a ray and rotate it a little bit. So this one right here, okay? So about a 30-degree rotation, let's say. So from the initial side to here, there's my little angle right there. I'm not going to name it because it's too small for me to write in. So this little pink one here is 30 degrees. I could also start my initial side and I could go all the way around the circle, 360 degrees, plus another 30, so 390 degrees would be this big angle here. I'll write it out here. So this big blue angle here, it's 390 degrees. And guess what? It lands up in the same place, right? So coterminal angle has the same initial. We started both of these angles at the positive x-axis and the same terminal side. In other words, the pink one, well, it was pink, stopped here initially, and then this blue one went around 360 degrees plus 30 and ended up in the same exact spot. That's a coterminal angle. And there are infinitely many coterminal angles because we can keep going around and around and around however many times we want, 360 degrees, to get the next coterminal angle. Okay, so I'm going to do a few examples of those to show you. Radian measure. This is really important because you're mostly going to be working in radians in this class and beyond. In calculus, that's all we do is work in radians. So this is pretty important stuff. Okay, so as we already said, the measure of an angle is determined by the amount of rotation, right, that we move our ray from the initial side to the terminal side, and we can measure angles in degrees or in radians. And degrees, I've been talking about degrees up here, right, 30 degrees, 240 degrees, whatever, but we need to start thinking about what a radian is and how we're going to measure angles in radians. So a really important definition is that 1 radian is the measure of a central angle. So a central angle is just, let me rewrite it here. A central angle is just an angle that's formed when the vertex, so hang on. So here's the plane, and I'm going to draw a circle. And this circle has some radius, we'll call it from here to here, right? The radius of a circle goes from the center of the circle to a point on the circle, so we just call it some radius r. Okay, now suppose I take that radius from the initial side here and I rotate it up this far. Then my terminal side is going to be here, right? So the angle that's formed, call it theta there, the angle that's formed is called a central angle, and it's called a central angle because the vertex is at the center of the circle. Okay, so whenever an angle's vertex is at the center of a circle, it's called a central angle. And those are really important because they help us do a lot of things, believe it or not, as you'll learn through the course. Okay, so the center of the circle is at the origin. The radius r goes from the origin or the center of the circle to any point. So this is a radius too. All the radii, any radius I draw here, any angle I draw, these radii are all the same. Okay, so by definition, a radian is the measure of a central angle. So this picture here has a central angle, even though it's a sad looking picture. Pretend that everything's perfect and that my vertex here is at the center of the circle, okay? That intercepts an arc S. So this angle here, the sides of this angle intercept, I'll get a different color. The sides of this angle theta intercept this arc, this piece of the circumference of the circle. And in this book, they call the arc length S, the letter S. So that's a letter S there. Okay, so 1 radian is the measure of a central angle that intercepts an arc S equal to the length of the radius. So if I were to measure this, and let's just say it was an inch, and then I measured an inch around here, and I put my 1 inch radius on top, that would be 1 radian, okay? And then I could do, you know, another 1 inch would be 2 radians, another 1 inch would be 3 radians, and so forth. And I'm going to show you in the book, because my picture doesn't do it justice. I can't draw, and I can't make anything like even look equal. But in the book, on page 261, there's a nice picture here. Okay, they're talking about, and even this one above is a lot nicer than the one that I drew. But here's our circle again, right? Here's our radius, because they're all the same. Our angle theta is here, and it intercepts this arc, which we're going to call S. Okay, and S is going to be equal to the length of the radius. But anyway, if I keep doing that, if I keep pasting these little radii around the edge of the circle, what's going to happen is it's going to look like this. So from the central, this is going to be a weird pencil, okay, it's from Hungary. But so here's our initial side, right? We always start at the positive x-axis, and we went ahead and we pasted a radius of some length r here, okay? So from here to here, we'd say that's 1 radian. Well, we could paste that same length from here to here. That's 2 radians. And we could paste that same length from here to here, which is 3 radians, and so forth, 4 radians, 5 radians, and 6 radians. So every circle here has a little bit more than 6 radians around it, okay? And in fact, it's about 6.28 radians, all right? So anyway, keep that in mind, and you're going to learn how to convert between degrees and radians and degrees, and so forth, okay? So let me remove the book. Now look, this formula is very important, and you have to memorize all of your formulas, okay? So the angle theta is equal to the arc length, which is this S, divided by r. And the arc length and the radius have the same units, so theta, this angle, is unitless. Okay, it doesn't have units. So if the length of this were, 1 inch, and the radius was 1 inch, well then the inches would cancel, and you just have 1 over 1 or 1. Okay, so you're just going to get a number out of that. But theta has to be in radians. We shorten that as rads. Okay, and that's acceptable. So this little ratio S over R is a real number. It has no units, okay, and it's equal to our angle measure. Now the circumference of a circle, the distance around a circle, if you were to walk in a circular path, is 2 times pi times the radius, okay? So 1 full revolution, 1 full spin, right, around this circle. So again, if this is my initial point, and instead of stopping here, I go all the way around, That's 360 degrees, okay? So 1 full revolution is equal to 360 degrees around the circle. So what I can say is, since the circumference is 2 pi r, then the arc would be the whole edge of the circle here, right? The whole way around the circle. So that would be my S. This whole thing would be S now. So that would be my arc length, the whole distance around the circle. So I can replace this C with S to represent 1 full revolution. So I can say the length of an arc for 1 full revolution is 2 times pi times r. So taking this formula here, right, I can say that S is 2 pi r, so I'm just replacing S with this thing, divided by r, and here the r's will cancel, so I get 2 pi. So your very first angle measure in radians is 1 full revolution, which is 2 pi radians around the circle, because it's equal, right? Our angle is equal to the arc length divided by the radius. Okay, so if I want to do a half revolution, like I did here, so I'm going to move this up. A half of a revolution, I start here and I rotate 180 degrees. I'm just saying that because you know what that is. Well, 180 degrees, or a half revolution, is just 2 times pi times r over 2 times r, right? So what I'm doing is I'm taking this formula, 2 pi r divided by r, and I'm multiplying it, let me write it here, by a half. So 1/2 times 2 times pi times r over r. And what happens is the r's are going to cancel, and the 2's are going to cancel, and I'm left with 1 times pi or pi. So that's why my little picture here, if I go 180 degrees, I'll just write that there. That's equal to pi radians. Okay, again, here's my full revolution here, which is 360 degrees or 2 pi radians. You need to know in degrees and radians that that's what that is. If I want to do a quarter of a revolution, like this picture here, so I went about a quarter, then all I have is 2 times pi times r over r times 1/4, right? So what's going to happen is the r's are still going to cancel, and I'm going to have 2 pi over 4, which reduces down to pi over 2. Sorry, wrong. I was looking at the 1/4 here. Yikes. 1/4 of a revolution. So this is a quarter, this is 2 quarters, this is 3 quarters, and that's 4 quarters, the whole, right? So anyway, this should be over here is pi over 2, or 90 degrees. Okay, and there's many others. There are several others that you're going to learn that are very common angles that we're going to use all the time. Here's 3/4, right? But how I find that is I can use that little formula, you know, that S is equal to 2 pi r over r, and just multiply it by the amount of rotation that I use, a quarter, a half, a third, whatever it is. The quadrants, as I said in class, there are 4 quadrants in the coordinate plane. We always write them counterclockwise, so 1, quadrant 2, quadrant 3, quadrant 4. And here I've labeled, you know, we start at 0. If my ray is here and I don't move it, it's 0 degrees. If I move it a quarter of a turn, right, this distance, then I've gone 90 degrees, or pi over 2 radians. If I move it 180 degrees, so this distance, that's 180 degrees, but we know it's the same as pi radians, okay, and so forth. So I've got quadrant 1, 2, 3, and 4 here, all right? If my angle lies in quadrant 1, it's going to be an acute angle. If I draw an angle from here to here, this is acute. Why? Because it's less than 90 and greater than 0, right? Acute angles are from 0 to 90, not including 0 and 90. If I have an angle in quadrant 2, because I always start at the positive x-axis, so I always start here. If I draw, let's say, this angle in quadrant 2, well, that's going to be obtuse. Why? Because this is bigger than 90 but less than 180, or bigger than pi over 2 but less than pi if we're talking about radians. Okay, and now I'm back to this finding coterminal angles and sketching. So let me get the book again and find some examples that we can go over. Okay, let me get some paper. All right, so in the book, on page 262, there are some examples about finding coterminal angles. And to find a coterminal angle, remember, you just add or subtract 2 pi. So if I want an angle coterminal to say pi over 6, I'm going to call this angle right here pi over 6, then what I have to do, well, there's a couple of things I can do. My other angle, I always start at the positive x-axis. I can go a full 360 degrees, which is 2 pi. This is in radians, so I need to be working in radians, right? So 360 degrees is 2 pi plus pi over 6. And I'm going to end up at the same terminal side. You see that? So I started at the same initial side and I ended at the same terminal side, so that's a coterminal angle. I could go around a couple of times. I could start on this side, so this is going to get ugly really fast. Well, here, let me make another. Here's another plane. I could start here again, so this is my pi over 6. I'm just going to put it out here, but that's the angle measure in here. But I could start at the same initial side and I could go around once. I could go around again. If I wanted to, I could go around again and then stop right there. So I've gone around 1, 2, 3 pi's, 3 times at 2 pi plus another pi over 6. So there's infinitely many of these because I can keep spinning that ray around and around and around the origin and end up at the same place as many times as I want. Likewise, I could start at the same initial side and I could rotate it this way if I wanted to and stop here and still have the same terminal and initial side. So every time I'm going to go around this circle, I'm going to add or subtract 2 pi. So here's some examples that you'll manipulate algebraically. It says, well, okay, it just says for the positive angle 13 pi over 6, subtract 2 pi to obtain a coterminal angle. Okay, so they're giving you a starting angle at 13 pi over 6, and actually I'm going to put the book back because there's a picture there. So I want you to find the coterminal angles. Let me just fix the camera here a little bit and fix the focus. Oh, there we go. Down a little bit more. Good. Okay. So what we've done is we take 13 pi over 6 minus 2 pi is going to give us pi over 6. Okay, so here's the picture that I wanted to show you, and you see everything's labeled in radians, so 0, pi over 2, pi, 3 pi over 2. Again, you need to memorize those. And look, the answer was pi over 6. We wanted to find an angle coterminal to 13 pi over 6. So they're showing you theta is 13 pi over 6. Well, that's this thing here. It's 2 pi plus this pi over 6. Make sense? So if I subtract 2 pi from 13 pi over 6, we get pi over 6. The other one in part B is for the negative angle, negative 2 pi over 3, add 2 pi to obtain a coterminal angle. So this theta here is 3 pi over 2, which is, I'm sorry, negative 2 pi over 3, which is the starting point, right? And if I add 2 pi to that, so in other words, I go around the circle one more time, I end up at 4 pi over 3. Well, how does that even work? Because some of you, your fractional skills are awful, but they're going to have to get good. So, adding pi's is just like adding fractions. If I want to add 13 pi over 6, or if I want to subtract 2 pi from 13 pi over 6, remember that this is over 1, right? I can't add or subtract depending on what my sign is. In this case it's subtract, but I can't subtract in this case because my denominators are not the same. So I have to make the denominators the same in order to add or subtract the numerators. So what I can do, this is an easy fix, I can multiply this fraction, 2 pi over 1, by 6 over 6, an equivalent fraction. So what I get is 13 pi over 6 minus 2 pi times 6 is 12 pi, and 1 times 6 is 6. Now my denominators are the same, so I can write that common denominator down, and you treat pi is a number, but for the purposes of adding or subtracting and leaving things in terms of pi, pretend it's an x. So think of what is 13x minus 12x? Well, it's just x. Well, 13 pi minus 12 pi is just pi, and that's how you get pi over 6. If I wanted to add 2 pi to 13 pi over 6, for instance, well, I'd have 13 pi over 6 plus 2 pi. Again, I have to make the denominators the same, so I'd multiply by 6 over 6. So we'd have 13 pi over 6 plus 12 pi over 6. And now my denominators are the same, so I write my new fraction with that common denominator. And now I'm adding the numerators, 13 and 12. Well, that's just 25 pi. 13 pi plus 12 pi is 25 pi. Okay. Maybe, you know, I want to find an angle coterminal to negative, I don't know, pi over 4. Well, negative pi over 4, as I start here, but I move, that's 45 degrees. I move this way. So I want to find an angle coterminal to negative pi over 4. Well, depending on which direction I want to go, do I want to go this way, right? Do I want to go around once? So I can add 2 pi to that, or I can subtract 2 pi from that. If I want to subtract 2 pi, well, that's just, again, my denominators are not the same, so I multiply to make them by whatever that denominator is, right? An equivalent fraction. So I have negative pi over 4 minus 8 pi over 4. My denominators are the same, so I can get negative 9 pi over 4. So I don't think the finding of the coterminal angles is going to be the problem. I think it's the fractions that are going to be the problem. And all you have to do is add or subtract 2 pi, and you're going to end up with the same terminal side, or in the same angle, or an angle coterminal to it that you had started with. Alright, I'm not going to have time to keep doing like tons of examples though, because tomorrow's parent conference night, and I'm trying to get this video done tonight because I'm not going to be able to do it tomorrow as I thought I would. Okay. So here was another example that I went over in class. We want an angle coterminal to pi over 6. So pi over 6 minus 2 pi, well, that's just, here's another way. Here's the way I really do it. I don't use equivalent fractions. I do 6 times negative 2 pi is negative 12 pi. That's a positive pi. And I rewrite it over the denominator, so I get a negative 11 pi over 6. You can always do that. Okay. So you're going to have some practice with those, and I'll answer any questions you have. I'm sure there's a billion videos on those online that you can also look at if you want more information on that. But again, I don't think it's the concept. I think it's going to be the fractions for some of you. Okay, complementary angles. Two angles are complementary if their sum is 90 degrees. Since we're working in radians, we know that 90 degrees is equal to pi over 2. So here I have, in quadrant 1, I have this angle alpha here, and then I have this angle beta. And if I add these two up, then they should add up to 90 degrees. So I would say alpha and beta are complementary, or alpha plus beta is equal to pi over 2. Supplementary angles, they sum to 180 degrees. I have an angle alpha here and an angle beta here. If I add alpha to beta, they should add up to 180 degrees, or in radians, pi. Okay? So sometimes you're asked to find the complement or the supplement of an angle in radians. So for example, this one says find the complement of 2 pi over 5. Well, if I'm trying to find the complement, then I know that this plus some other angle has to equal to pi over 2. So it just makes sense to subtract what they're giving me from pi over 2. So that's what I did. Pi over 2, 90 degrees, minus 2 pi over 5. Again, my denominators are not the same. So what I said in class is if you're completely clueless on the whole denominator thing, which you need to get over and you need to figure that out, especially if you're going to calculus next year. You should not be going into calculus if you cannot simplify a fraction. But when worse comes to worse, you can multiply the bottoms, the denominators together. So 2 times 5 is 10. And then cross multiply. 5 times pi is 5 pi. Bring down whatever sign is originally there, here, and then 2 times 2 pi is 4 pi, and now my denominator is the same, so I can add or subtract the top. So 5 pi minus 4 pi gives me pi over 10. So pi over 10 is the complement of 2 pi over 5. This one says find the supplement of the same angle. Well, what I know is that this angle plus some other angle has to equal to 180 if they're supplementary. So I'm going to subtract it from pi. Pi minus 2 pi over 5, that's just 5 times pi, which is 5 pi, minus 2 pi, all over 5, all back over that common denominator. Now I can subtract the numerators and get 3 pi over 5. Degree measure. This is something you're probably a little more familiar with from geometry. You probably remember some stuff from geometry. But it's another way to measure angles. We rarely use it though in trig. Okay? And 1 degree, so remember, we have this circle, right, whose center is at the origin of the plane. That's the center of the circle. And if I start at the initial side and go all the way around, that's 360 degrees, right? So what that means is 1 degree is 1/360th of a rotation. So 1 degree would be like there. This distance right here would be 1 degree. Even smaller, but I can't draw that small. So anyway, 1 degree is 1/360th of a rotation of a complete revolution. So, and again, about the vertex or about the center, right? So again, 360 is 1 complete revolution, a half revolution. So 360, here's 360, right? 1 whole sweep around. 180, I start here and I end here. So that's 180 degrees. It's a semicircle. A quarter revolution, I would start here and swing up here. That would be 90 degrees, okay? So 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then 360 degrees, right? 180 and 90. So we know that 360 degrees equals to 2 pi radians, right? Those are full revolutions. And 180 degrees equals 2 pi radians. Since 1 degree is equal to pi over 180 radians, it makes sense that 1 radian would be equal to 180 over pi. So you notice these two, they're just the reciprocals of one another. So it's super easy to convert from degrees to radians or radians to degrees. Okay? So if you want to go from degrees to radians, you just multiply by pi over 180. And if you want to go from radians to degrees, you multiply by 180 over pi. So let me find a couple simple ones, and then you can look at these, which I went over in class. So let's say we want to convert, we want to take, say, 45 degrees, and we want to convert it to radians. Okay? Well, the rule is very simple. I take my degrees, and I multiply it by pi radians over 180 degrees. I want you to notice that I've got degrees, so this is over 1 if you want. Degrees are on the top here and on the bottom here, so those units are going to cancel. And what am I left with? Radians. Now I can say, are there numbers that divide evenly both into 45 and 180? Well, there are, right? 45 degrees goes into 184 times. 45 goes into itself once. It goes into 184 times. So if I clean this mess up, I'm going to have 1 times pi radians, which is pi radians, over 1 times 4 is 4. So 45 degrees is equivalent to pi over 4 radians. If I want to convert 60 degrees to radians, well, then I would have 60 degrees times pi radians over 180 degrees. So I keep using the same ratio, pi to 180. Again, the degrees are going to cancel out, right? Radians is going to stay. I can cancel a 0 on the top for a 0 on the bottom. I know that 6 goes into itself once, and it goes into 18 3 times. So, and again, put that over 1 if you want to. In the numerator, I'm left with 1 times pi radians. So I have pi radians on top. And on the bottom, I have 1 times 3, or 3. So 60 degrees is equal to, oops, well, we'd actually write it, that was terrible, pi over 3 radians, or rads. Okay, let's do one more. Degrees to radians. So, I don't know, let's say 160 degrees. We want that, we want to convert that to radians. So it would be 160 times pi over 180. Again, I can cancel a 0 for 0, so that's going to give me 16 pi over 18. And now I want to, remember, you always have to reduce the numerical part. So I want to see, you know, what is a number that divides evenly into both 16 and 18? Well, you know, 16 is 4 times 4, or 2 times 8, right? And 18 is 9 times 2, or 6 times 3. So if you want to, you know, you can break those down into factors, but I would start with 2's because they're even. You know, you could say 2 goes into 16 8 times, and 2 goes into 18 9 times, and that's going to leave you with 8 pi over 9. Now when I look at 8 over 9, I can't reduce that, so I leave it alone. I'm done. So I know that 160 degrees is equivalent to 8 pi over 9 radians. I'll put my rads. Let's do sum from radians to degrees. So maybe I want to convert 5 pi over 4 to degrees. Okay, well, the rule says that, you know, if we're going from degrees to radians, we multiply by pi over 180. If we're going to go from radians to degrees, we just flip that. So all I have to do is 5 pi over 4, I'll put radians here, times 180 over pi radians. What's going to happen is the radians are going to cancel, the pi's are going to cancel. So the idea is when you're going from radians to degrees, you need to get rid of pi. So one needs to be on the top and one needs to be on the bottom. So that's a way to remember it. And anyhow, what we're left with is 5 times 180 on the top over 4. And now I can start to see, you know, hey, these two numbers are even. Maybe I can find a number that divides evenly into 4 and 180. Well, there is, right? 2. 2 goes into 4 twice. 2 goes into 180 90 times. So that leaves me with 5 times 90 over 2. And hey, 2 goes into itself once, and it goes into 90 45. And if I multiply, so this is over 1 now, so I don't need it. But on the top, in the numerator, if I multiply 45 times 5, 5 times 5 is 25. If I carry over the 2, I get 225 degrees. Sorry about that. So 5 pi over 4 radians is equal to 225 degrees. Maybe I want to know, maybe I want to convert, well, let's do 90 degrees. 90 degrees, pi over 2 radians to degrees. Well, that's pi over 2 times 180 over pi, right? Because those pi's have to cancel, cross cancel. So it's easy to see the pi's are going to cancel. So I have 180 over 2. If you like to write it that way, you can do that. And I know that 2 divides into itself evenly once, and it divides into 180 90 times. That gives us 90 degrees. So 90 degrees is equivalent to pi over 2 radians. Let's do, I don't know, 4 pi over 3. No, I don't want to do 4 pi. Let's do 7 pi over 3. Radians to degrees. That's 7 pi over 3 times 180 over pi. You notice I'm leaving out the radians now, or the degrees, because they're going to cancel anyway. So you don't have to show that those are canceling. The pi's are going to cancel. And I say, hey, 3 goes into itself once, and it goes into 180 60 times. So what am I left with in the numerator? I'm left with 7 times 60 all over 1, so you don't have to write that. There's nothing to cancel, so I just have to multiply 7 times 60. Well, 6 times 7 is 42, but I have to add that 0 there because it's 60 times 7. So 420 degrees is equal to 7 pi over 3. By the way, 420 degrees, just think about that. Where is it? Well, I would have to go around, so I'd take my ray here, my initial side. I have to go 360 plus how many more to get to 420? Well, all I have to do is subtract 1 revolution from that. So I'd have to go around a whole 360, right? Plus another 60, so 60 degrees is like right about here. So I have to go all the way around 360 plus 60 more. That whole angle right there is going to be 420 degrees, or 7 pi over 3. And it makes sense, right? Kind of. When you think about the outside of the circle, where the radian measure is equal to the arc length is equal to the measure of the radius, right? We had 1 radian, right? Another radian, right? There were 6 and a little bit more, right? 6.28 radians. So it makes sense that 420 degrees would be 420 degrees, or 7 pi over 3. This is a little bit more than 6 right here. This is 6.28, and we were at 60 degrees, so it makes sense. Another radian is 7, right, and a third. So you can think about it that way too. Let me see what else was in here. Oh yeah, the arc length. So every circle, you can find the arc length of a circle. Okay. So let me draw a circle. Bad circle. The arc length of a circle, usually in geometry, the arc length we would write as L is equal to our central angle divided by 360 times 2 pi r times the circumference. Because remember, if I swing this initial side to say here, then this angle theta is going to intercept this arc right here, which we call S, right? But anyway, when we work in radians, we're not going to use that formula because that's in degrees. So if we can remember that a radian is defined as the arc length over the radius, I can take this little equation and solve for the arc length, which is S. So I can multiply both sides by r. Those are going to cancel. So I get S is equal to r times theta. R is the radius, theta is the angle measure. Okay? And remember that theta is always a central angle too. So the length of an arc is r times theta, but theta has to be in radians. Okay? So, for instance, if I want to find, say I give you this picture here of a circle, and let's just say this is pi over 4 radians. So the measure of this angle is pi over 4, and I want you to find this arc length here. Well, and maybe let's say the radius is 2. So the radius is 2. Well, I would say that the arc length is equal to the radius, which is 2, times my angle, right, which is going to be pi over 2. That's the length of this, this piece of the outside of the circle, or the edge of the circle. The arc of the circle is what it's called. Okay, in the example in class, we were given a radius of 4 inches. This problem's in the book. Okay, they tell you to find the length of the arc intercepted by a central angle of 240 degrees. Well, that's all nice, but remember, we have to be in radians, so the first thing I have to do is convert this 240 degrees into radians. So I have to multiply by pi over 180. Again, I can say, a 0 cancels with a 0. I can say that, what's a number that divides evenly into 24 and 18, right? Well, 6. 6 goes into 24 4 times, and 6 goes into 18 3 times. So I'm left with 4 pi over 3. So this is my angle measure in radians. And then according to my little formula, I know what the radius is. It's 4. They told me it was 4. So I can find the length of that arc. It's 4 times 4 pi over 3, which is 16 pi over 3. And I know when you're thinking about measurement, it's kind of hard to imagine, like, what is 16 pi over 3, inches or feet or whatever. So you use your calculator. It's about 16, almost 17 inches. So that gives you something to, wrap your mind around. You say, oh yeah, I understand about how long that is. It's harder to do when it's in radians, so you can always use your calculator to kind of get an idea of how the length is linearly. And I believe that was the last page. So I went over that kind of quick, but this is the third time today, so I'm a little tired of it. So anyway, try the homework I wrote up on the board for you, and if you have any questions, you can ask me on Friday, the day before a nice long week break. All right, have a great night. See you Friday.